Alright, welcome back, Digital Electronics. Today we're going to cover octal and hexadecimal systems. We're going to be doing the same kind of procedures that we did when we did binary to decimal, decimal to binary. Now we're going to be going like octal to decimal, hexadecimal to decimal, and back and forth. Just a different type numbering system where we transmit data using like a hex system and things like that a lot more. Okay, so you and I as humans, we use the decimal system, right? So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, so on and so forth up to infinity. Well, computers, we have to convert those numbers into some sort of binary form. When we do that, we use an octal or a hexadecimal system. So, most of our computers use, this is a little outdated here with 32 and 64 or 128-bit buses. We're around 256, 512 buses and things like that with where we're at. So, but if you look like a 32-bit data transmission, all right, so it's 0, 1, 1, you can read the entire line out there. Okay, that's 32 bits of data. So if we have like something that's like a 256-bit encryption, all right, you can imagine how large that number is going to be and how hard it is to crack when you use 256-bit. And that sort of thing. So we're going to use these to represent binary numbers. We're going to use a hexadecimal system, which is base 16, and the octal system, which is base 8. In our decimal system, that's base 10, right? And remember, binary is base 2. So we're going to take all these binary numbers and truncate them into hexadecimal and octal numbers so that we can transmit more data at a time. Okay, so decimal. When we did decimal to binary, we did successive division by 2. When we went binary to decimal, we did weighted multiplication, right? We used the base 2. You did 2 to the 0, 2 to the first, 2 to the second, 2 to the third, so on and so forth. Okay? If you don't remember that, maybe go back and watch the binary as well. Okay, so it's going to be, the operations are going to be very, very similar here when we do this. So when we do octal, we're going to do successive division, but we're going to do successive division by 8 now, because 8 is the base. Our weighted multiplication is going to be with base 8. So we're going to start with 8 to the 0, 8 to the first, 8 squared, 8 cubed, 8 to the fourth, so on and so forth. Okay, and then kind of the same approach we're going to take with hexadecimal. Still successive division, but now we're going to divide by 16. All right, in our weighted multiplication, we're going to have 16 to the 0, 16 to the first, 16 squared, 16 cubed, so on and so forth with that as we're going back to decimal. So this is your roadmap to be able to go from decimal to octal, binary, or hexadecimal, or to go from octal, binary, hexadecimal back to decimal. All right, that's essentially what a roadmap is. Look at our hexadecimal numbers there. We've reviewed them a little bit, but notice we go 0 through 9, and then we can't use any more digits, so we're going to use A, B, C, D, E, and F. So A is equivalent to 10, B is equivalent to 11, C is equivalent to 12 for us, D is equivalent to 13, E is equivalent to 14, and F is equivalent to 15 for us. So 0 to 15 is 16 digits, okay? Notice at octal is 8 digits starting at 0, so it's 0, 1, 2, 3, 4, 5, 6, 7. So make sure that we're understanding octal is 8 digits, hexadecimal 16 digits. And we can represent hexadecimal with letters. So sometimes when you're booting up your computer, you can see like a hexadecimal number or two flash across the bottom of the screen. That's really what you're looking at there. Okay? So we can look at this table here, and we can see all the, I'm not going to go through each one individually, but you can see the decimal number that you and I use in everyday math. All right, it's binary equivalent, it's octal equivalent, and it's hexadecimal equivalent. Notice about octal, it goes 0, 1, 2, 3, 4, 5, 6, 7, and then it becomes 1, 0, 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7, then has to start over at 2, right? Because remember, octal is only 8 digits, and those digits can only be 0 through 7. So when it goes 0, 1, 2, 3, 4, 5, 6, 7, the next number read is 1, 0, not 10. It's 1, 0, 1, 1, 1, 2, 1, 3. Read it as such. Okay, hexadecimal, we already kind of discussed this. All right, letters. Then what happens after we get to F? 16 becomes 1, 0 in hex. Okay, 1 1, 1 2, 1 3 in hex. Okay, so we got to pay attention and understand this table and how the different numbers relate as we go through here. Okay, so this is just reviewing the map that we had before. Alright, so if our decimal was base 10, we did successive division by 2 to get to our binary numbers. Okay, and then when we did our binary to decimal, we did 2 to the 0 times the bit, and 2 to the first times the bit, 2 squared times the bit, 2 cubed times the bit, 2 to the fourth times the bit, and then we added all those up. We're going to do the exact same thing here. So octal is going to do the same thing. Okay, and we can do the same approach with any base. You know, say there was a base 12 or something like that that we don't use. You would do the exact same thing. Division by that number, okay, and then that number raised to the powers multiplied by the bit when we have the decimal. Okay, it'll make sense here as we do the examples here. So when I'm talking successive division by 8, okay, it's just like we did before, and then we have to pay attention to what's the LSB and what's the MSB, and then we write the digits from MSB to LSB. Alright, so let's look at this example here. We're going to take the number 94 with a subscript 10, so that tells me it's the number 94, not 94 hex, but it's a 94, and the subscript 10 tells me it's decimal, and I'm going to do that into its octal equivalent. So I'm going to take the number 94 and do successive division by 8. So I'm going to take 94 divided by 8. Okay? The best thing I can get is 11, because 11 times 8 is 88. 94 minus 88 is 6, so our remainder is 6. Then I take the number 11 and divide it by 8. 8 goes into 11 one time. Okay, so 11 minus 8 is 3, so our remainder is 3 there. Then I have to take 1 and divide it by 8. That can happen 0 times, so then my remainder is 1. So as always, the last number I get is my MSB. The first number, remainder that I got was my LSB. So I write this in terms of MSB to LSB. So this number becomes 136 octal. Alright, so 94 decimal is the equivalent of 136 octal. And you write the subscript 8 there so that you know that it's octal. Alright, so I want you to pause the video, try this one on your own, and then I'm going to go ahead and start it up here. So pause the video, do it on your own, and then come back and we'll be working through it together here. Alright, so we want to take the decimal number of 189 to its octal equivalent. So we're going to do successive division by 8. Okay, so when we do that, what we'll do is 189 divided by 8, 23 goes in the most, and that 23 times 8 is 184. So 189 minus 184 is 5. So that's where the remainder 5 comes from. Okay, and that's going to be our LSB. Then we're going to take 23 and divide it by 8. Okay, 8 goes into 23 2 times. That's 16, right? 8 times 2 is 16. 23 minus 16 is 7, so our remainder is 7. And then I take 2 and divide it by 8. It goes in 0 times, so my remainder is 2. So that's my MSB. So I write this from MSB to LSB. So it's 275 octal. Alright, so let's go the other direction now. Now I'm going to give you an octal number, and you need to write that in its decimal form. So this example is just showing you how to go the other direction of the one we just worked. Okay, so octal, you're given 136 in octal, and so we're going to do successive multiplication with the base of 8. So 8 to the 0, 8 to the first, and 8 squared. So we're going to take 8 to the 0 and multiply it by 6. So 8 to the 0, anything to the 0 power is 1. 1 times 6 is 6. So you write 6 down there. Then we're going to take 8 to the first, which is 8. And then 8 times 3 is 24. So you write down 24. And then we're going to take 8 squared, which is 64, and multiply it by 1. 64 times 1 is 64. Then we add those up. 64 plus 24 plus 6 is 94. Okay? So you're going to take your bit weighting factor and multiply it by the original octal value once you get it. And you have to do that for every octal value you have, and then you add them all up. So we can see how to go back and forth. Alright, so why don't you guys pause the video, try and do this one on your own. Okay, if you can't, that's okay. I'm going to work through it for you. So go ahead and pause it, do it, and then come back and work it with us here. So we're going to take 134 octal, so 134 octal to its decimal equivalent. So I got to break that up, and I'm going to take 4 times 8 to the 0 plus 3 times 8 to the first, and 1 times 8 squared, and then I'm going to add all those up. Okay, remember the base is 8, that's why we're doing it that way. So 8 to the 0 is 1, 1 times 4 is 4. 8 to the first is 8, 8 times 3 is 24. Alright, 8 squared is 64, 64 times 1 is 64. And when I add all those up, 64 plus 24 plus 4 is 92 in decimal. So there's how I've gone from octal to decimal. Alright, now we're going to do hexadecimal. We got to get a little bit better with our, our multiplication in this case. So the steps are the same. We're going to take whatever number we have in decimal and divide it by 16 and write out our remainders. Okay, so we're going to take this decimal number 94 now and write it in terms of hexadecimal. Okay, so I'm going to take 94 divided by 16. Well, the best number that goes into that is 16 times 5. So 16 times 5 is 80. Okay, that's the closest we can get to 94 without going over 16. So we have to take 94 minus 80. That's 14. If you look back to the table, okay, which I'm showing right here, we can see that the letter E under hexadecimal is equivalent to the number 14 under decimal. So you guys can see that here when we look back at this table. So we can write our remainder as 14, but since we're writing it in hex, we have to write it as E. Okay, so our remainder is 14, but converted to hex, or transferred to hex, okay, 14 is E. So our LSB there is E. Now we're going to take 5 and divide it by 16. It goes in 0 times, so our remainder is 5. That's our MSB. So we're going to write this in terms of MSB to LSB. So 94 decimal is the same as 5E in hexadecimal. Alright, so why don't you guys pause the video, work through this example on your own, okay, and see if you can get it. So remember, you got to do successive division by 16. Alright, so when we do that, we get successive division by 16. The best we can get is 16, okay, goes into 429 26 times. Okay, so 16 times 26 is 416. So 429 minus 416 is 13. We don't write 13, we write the letter D. Okay, because going back to that table that I had in the previous slide, that's what that is. So our remainder is 13. So now we got to take 26 and divide it by 16. It goes in one time, okay, and then 16 times 1 is 16, so you got to take 26 minus 16, which is 10, but we don't write 10 in hexadecimal, we write the letter A, because in the table, A is equivalent to 10. So you're going to have to reference back to that table a few times as you guys start going through this, that table that's on slide 4, okay? Then we have to take 1 and divide it by 16. It goes in 0 times, so our remainder is 1. So our MSB is 1, our LSB is 13, and when we write this out from MSB to LSB, we're going to get 1AD, and then there's a subscript H, alright, it means hexadecimal. We can write hexadecimal two ways. We can write subscript 16, or we can write it as subscript H, alright, it means the same thing to us when we do this. Okay, in the last part of this, we're going to go the other direction now. Okay, I'm going to give you the hexadecimal number, and you're going to convert it to decimal. We're going to use the base of 16. So we're going to take 16 to the 0 and multiply it by its bit. We're going to take 16 to the first. multiply it by the bit, 16 squared, multiply it by the bit, so on and so forth. 16 cubed, multiply it by the bit. Okay, so we're going to take the example 5e, which is what we just we found in the previous example, right? We went 94 to 5e. We're going to go back the other way so that you see that it works. So we're going to take 16 to the 0 times e. 16 to the 0 is 1. Remember, anything to the 0 power is 1. E is 14. So we're going to take 1 times 14, and we're going to get 14. Then we're going to take 16 to the first, which is 16. 16 times 5 is 80. So we can take 80 plus 14, and that gives us 94 in base 10. Okay? Alright, so you guys, why don't you pause the video, try to do this example, and then when you unpause it, we'll be working it out together. Alright, so we have the hexadecimal number B2EH, and we want to send that to its decimal equivalent. Alright, so we're going to take 16 to the 0 times e, 16 to the first times 2, and 16 squared times b. Alright, so we're going to work this out. So remember, e is equivalent to 14, b is equivalent to 11 when we work through this. So 16 to the 0 is 1. Anything to the 0 power is 1. 1 times e, e being 14. So 1 times 14 is 14. Alright, we're going to take 16 to the first, which is 16. 16 times 2 is 32. Alright, and then we're going to take 16 squared, which is 256, and we're going to multiply 256 times b. Remember, b is 11, so 256 times 11 is 2,816. And then we're going to add all those up. So 2816 plus 32 plus 14 gives us 2862 decimal. So B2EH, right? B2E in hexadecimal is equivalent to 2862 in decimal. Alright, so hopefully you're able to work through that successfully. Alright, now let's do another one. We're going to go 5AH to octal. So we're going 5A hexadecimal to its octal equivalent now. Okay, so when we do this, we're going to convert back and forth. So we can take 5A and we can put it into its decimal. Alright, so we're going to take 5A and put it into its decimal. So we're going to take 16 to the 0, which is 1. 1 times A is 10. So we're going to get 1 times 10 is 10. We're going to get 16 to the first, which is 16. And then 16 times 5, which is 80. So we're going to get 80 plus 10 is 90. So that is 90 in decimal. Okay, and then we're going to take that decimal number and put it into octal. So we're going to have to do successive division by 8. So 90 divided by 8, the most whole number is 11. So 8 times 11 is 88. 90 minus 88 is 2, so that's our LSB. Then we're going to have to take 11 and divide it by 8. 8 goes in one time. We have a remainder of 3. And then we're going to have to take 1 and divide it by 8. It goes in 0 times, so we have a remainder of 1, which is our MSB. So remember, we write that out as 132 with a subscript 8. So it's a 132 octal. Alright, so 5A in hexadecimal, we had to convert it to decimal, and then we took that decimal and converted it to octal, ended up giving us 132 in octal. Okay, now let's convert this octal number to its binary equivalent. Okay, so first of all, when we do this, we have to take it and put it into decimal. So we're going to take 132, put it into decimal by using our base of 8. So 8 to the 0 is 1. 1 times 2 is 2. 8 to the first is 8. 8 times 3 is 24. Okay, and 8 squared is 64. 64 times 1 is 64. Adding all those up, it's 90 in decimal. And then the last part you already know how to do. Successive division by 2. So we were able to take that decimal number and put it back into binary. So 90 divided by 2 is 45 with a remainder of 0. Then 45 divided by 2 is 22 with a remainder of 1. Okay, 22 divided by 2 is 11 with a remainder of 0. 11 divided by 2 is 5 with a remainder of 1. 5 divided by 2 is 2 with a remainder of 1. Okay, 2 divided by 2 is 1 with a remainder of 0. And 1 divided by 2 is 0 with a remainder of 1. So remember, we've got to write this out MSB to LSB. So when we do that, we get 10111010. Alright, so that's taking that octal number and converting it to decimal. So it's 2 steps. Alright, convert it to a common number that's a decimal number, and then we can convert that decimal number back to binary. Okay, now there is a shortcut if we understand octal is really 2 to the 3rd, which is 8. So we can chunk our binary groups in chunks of 3. When we do that, okay, we can convert them to octal. So let's start with this binary number that we just calculated, which is 10111010. That's a binary number. If we start on the right hand side and group it into chunks of 3, so we get 010, then we get 011, and then we get 1. But in front of that 1 is 2 zeros, so 001. Okay, 001 translates to a 1 in octal, 011 translates to 3, and 010 translates to 2. So 132. So that binary number of 1011010 translates to 132 octal. Okay, you can put as many zeros in front of the number as you need to make sure that this gets completed. Okay, so we group them in chunks of 3 when we're going binary to octal. If we're going binary, okay, to hex, we have to group in chunks of 4. Because remember, hex, the base is 16, which is really 2 to the 4th. 16, so 2 to the 4th bits. Okay, so 16 bits, that's where that comes in, where it's calculated from. So instead, we're going to take that number 1011010, it's binary, and we're going to convert it to hexadecimal by grouping it in chunks of 4. So the first number we group into a chunk of 4 is 1010. If you look at the table back on slide 4, that translates to the letter A. Okay, if we have 0101, looking back at the table, that's hex, it translates to the number 5 on the table on slide 4. So make sure you got a copy of the table on slide 4 working with you as you go through these examples. Alright, so let's do another example here. We're going to use that shortcut technique here to convert the hexadecimal number A16 into its binary and octal equivalents. Okay, we can use the calculator if you want to check the answer. So let's write these things down. And how do we approach this? Well, you got to remember what A is in hexadecimal. We need 4 digits for A. Okay, A is equivalent to the decimal number 10. So we want to go back and look at the slide on, the table on slide 4. So if we're looking here at the table, this is back on slide 4. If we look at hexadecimal A, which is equivalent to decimal number 10. When we write it in binary, we write it as, you can either write it as 1010, or it depends on how many bits we need, you can write it as 01010. Okay, so we're just looking at what A equivalent decimal is. And then 6, we have to write that in binary, that's 00110. Alright? So now that we've kind of taken a look at the table, so when I put this on the screen, it's going to make a little bit more sense here. So A in binary is 1010, 6 is 0110, and when we string all that out together, that's A6 in hexadecimal converted to binary. We can take that same binary number now and group it into chunks of 3. That will give us our octal. So we're using the shortcut method here. So I can use 110, 100, and 010. 110 is equivalent to 6 in octal, 100 is equivalent to 4 in octal, and 010 is equivalent to 2 in octal. So that binary number 101001110 translates to 246 in octal. So I think once you guys get down the shortcut method, going binary to hex, hex to binary, or binary to octal, octal to binary, it's much easier, much quicker than doing the successive division by 2 sort of scenarios. But that's it for this lecture. So like I said, if you have questions, email me, ask me if you need a team meet or a Zoom meet. Else, I'll see you guys in class. Have a great day.